Welcome back to the deep dive. If you've been following AI over the last, I don't know, couple of years, you know that the transformer architecture has just been king.
It's been the default for everything.
Exactly. But today, we are cracking open the paper that really challenges that reign. It's titled Mamba, Linear Time Sequence Modeling with Selective State Spaces.
Yeah, published in 2023 by Albert Gu and Tridao, and it is, I think, truly landmark research.
So our mission, as always, is to take this pretty complex paper and just distill it down, make it clear and understandable.
Right. Whether you're an engineer, a student, or you're just, curious about this stuff, we want you to walk away getting why this model is forcing a total rethink of how we build these things.
And we spent so much time on this show charting the rise of the transformer, right?
Yeah.
We started with attention is all you need.
The one that started it all.
Then we looked at BERT for, understanding language, GPT-3 for that massive scaling and few-shot reasoning, and even CLI for mixing language and vision.
The transformer was the answer for everything.
But Mamba feels like a turning point. It's this moment where researchers started asking, wait, should transformer remain the default?
Yes. The problem was never the quality. Transformers are amazing at what they do. The problem is, and has always been, efficiency and scale. Mamba is basically trying to fix the transformers, its crippling computational drawback.
Okay, let's unpack that, the drawback.
Yeah.
Why is the transformer so expensive? And I guess why did everyone just accept that cost for so long?
It all comes down to the attention layer. Its genius is that it can route information so densely. Any token in a sequence can look directly at any other token instantly.
So the beginning of a document can connect to the end no matter how far apart they are.
Exactly. And that's what gives it such powerful context. But that power comes with a huge price tag.
A very severe one.
It really is. You get hit with two massive limits. First, you have a finite context window. The models can only look at so much data at once. But the real killer is the scaling.
The computational cost.
Right. It scales quadratically. That's O of L squared, with L being the sequence length.
And for anyone who might not remember their computer science classes, quadratic scaling it's just brutal. If I double the length of my text, say from a paragraph to a page, I don't just double the cost.
No, you quadruple it. Double the sequence again to, a few pages, and suddenly you're at 16 times the cost. It's unsustainable.
And when you're trying to process huge documents or video, or as we'll see with Mamba, like genomics data, that O of L squared just becomes an architectural ceiling, you can't get past it.
You literally hit a wall.
So if the transformer hits this quadratic ceiling, where do we look?
Yeah.
This brings us to the alternative, right?
Yeah.
State space models or SSMs.
Exactly. And SSMs have been around for a bit, especially a version called S4, which stands for Structured State Space Sequence Models.
And they're sort of a hybrid.
Yeah, they take ideas from both RNNs, recurrent neural networks, and how they evolve a state, and also from CNNs, convolutional neural networks, and how they can be parallelized.
And the big win here is efficiency. That's the whole point.
Massive efficiency. Unlike the transformer, SSMs scale linearly, or, close to linearly. O of L.
So if you double the sequence length,
you just double the cost. It's predictable, it's manageable, it makes them a potential game changer for really long sequences.
Okay, but if they were so fast, why did they take over before now? There has to be a catch.
There was a big catch. It was about where they succeeded. These earlier SSMs were great on benchmarks like the long-range arena, and they were fantastic with continuous data. Think audio waves or pixels in an image.
But not text.
But not text or code. When it came to that kind of discrete, information-dense data, they just couldn't match the quality of transformers. They weren't as good at language.
And that leads us right to the genius of Mamba. This is where they figured out how to close that gap. Why did those older SSMs struggle so much with text?
So the limitation was, it was conceptual. The prior models were something called linear time invariant, or LTI.
That sounds dense.
It does, but the idea is simple. It just means their internal rules, the parameters that controlled their memory, were constant. They were fixed for the entire sequence.
Wait, so they treated the first word with the same importance as the last word, and every word in between.
Precisely. They lacked content awareness. When you read something, you instinctively skip filler words, but you latch onto important things like a name or a date. You need to be selective. An LTI model can't do that because its parameters never change based on what it's reading.
That's like trying to take notes in a lecture, but you have to write down every single word the professor says without knowing what's actually important.
Perfect analogy. You can't prioritize. So Mamba's core innovation is what they call the selection mechanism. They realized they had to break that time invariance.
Oh.
They made some of the key SSM parameters, specifically one called delta or AWA, and the input and output parts. They made them functions of the input.
So they're not constant anymore. They change depending on the token the model's looking at.
Exactly. Now the model can decide on the fly what to remember and what to forget, just like that student taking selective notes.
Okay, tell me more about this delta parameter. That sounds like the key.
It's the most important piece. It basically acts like a souped-up gating mechanism, kind of like the gates in old-school RNNs like LSTMs.
So it opens and closes based on the input.
Sort of. The model calculates a new delta for every single token. If it decides the current token is just noise or filler, it generates a small delta.
And a small delta means?
It means the internal state persists. It basically ignores the current input and just remembers what it was already thinking about.
But if it sees something crucial,
It generates a large delta. And a large delta forces the model to reset its state and focus heavily on that new important input. It forgets the irrelevant history and memorizes the new thing.
so that dynamic switching is what gives it the content-based reasoning that the older models were missing.
That's the whole trick. And they prove this on these really clever synthetic tasks, like the selective copying task.
Which sounds like it was designed specifically to break the old LTI models.
It absolutely was. The task is to memorize specific tokens that are buried in a sea of irrelevant noise. The LTI models just get overwhelmed, but Mamba,
It just filters out the noise.
effortlessly, it copies the important stuff perfectly. And then there's the induction heads task, which is super relevant for large language models.
Because that tests associative recall, right? The thing
Yeah.
that powers in-context learning.
Yes. And what's just mind-blowing here is Mamba's ability to extrapolate. They trained a small Mamba model on sequences that were only 256 tokens long,
Okay.
and then they tested it on sequences up to 1,000,000 tokens long.
1,000,000. And it worked.
It worked perfectly. It generalized to data that was 4,000 times longer than anything it had ever seen in training.
That's a huge deal.
Right.
Transformers just can't do that. They run out of memory, or they just fail to generalize past their training length.
Right. So Mamba solved the quality problem. Selectivity gives you the content awareness, but in doing that, they created a massive, massive engineering problem.
Oh, of course. There's always another problem.
By making the parameters depend on the input, they broke the efficient parallel computation that the older SSMs used.
Wait, so they fixed the quality flaw, but they accidentally broke the speed advantage. How did they fix that?
This is where the paper gets really brilliant, I think. It's the hardware-aware solution. A simple recurrent calculation would be incredibly slow, not because of the math itself, but because of memory.
You mean moving data around on the GPU chip?
Exactly. The GPU has two kinds of memory. You have the big, slow off-chip memory called HBM, and then you have the tiny, super fast on-chip memory, the SRAM.
And the bottleneck is always moving data from the big, slow memory to the fast cache.
It's always the I/O, the input-output. So the goal became, how do we do all the heavy lifting in that fast SRAM without constantly going back to the slow HBM?
And their solution was?
A new parallel algorithm they call the selective scan. The trick is something called kernel fusion. They basically merge all the key steps, the math for delta, the scan itself, the output into a single operation.
An operation that can run entirely within the fast on-chip memory.
Exactly.
Yeah.
It dramatically reduces the number of times you have to read from and write to that slow memory. And then they used another clever trick in the backward pass called recomputation.
Instead of saving everything, they just recalculate it when they need it.
Right. It saves a huge amount of memory. The end result is that Mamba's memory footprint is now on par with a super optimized transformer using something like flash attention 2.
But the underlying math scales linearly, not quadratically. That is a revolutionary piece of engineering.
And it has huge implications for inference. When the model is actually being used, Mamba is constant time per step when it's generating output.
Which is where transformers really struggle with that KV cache.
Yes, the key value cache in a transformer has to store information about every previous token, and it just grows and grows. Mamba doesn't need that.
So what's the bottom line in terms of speed?
The bottom line is Mamba achieves up to 5 times higher generation throughput than a transformer of the same size. 5 times. That's an enormous win.
And this efficiency lets them simplify the whole model design too, right?
Massively. The Mamba architecture is just a simple single stack of these selective SSM blocks. It doesn't use attention layers at all. It doesn't even need the typical MLP blocks you see in
It's
transformers.
just simpler. A simpler architecture that's also more efficient and performs better.
It really is the headline. Mamba is the first linear time model to actually achieve transformer-level quality on language. Their 3 billion parameter model matches the quality of transformers that are twice its size.
So, a Mamba 3B model can beat a Pythia 7B model on common sense reasoning.
Exactly. You get more performance per parameter while also solving the scaling problem.
That completely changes the conversation. It's not, do I sacrifice quality for speed anymore? It's, can I get better quality because I'm faster and can handle way longer context?
And the long context validation proved that out. Look at DNA modeling. It's the perfect stress test. Insanely long sequences where you need to find dependencies millions of tokens apart.
And Mamba could handle context lengths up to 1 million tokens on the human genome.
1 million tokens. And on this really tough classification task, trying to distinguish between great ape species where the DNA is like 99% identical, Mamba's performance just kept getting better and better as the context length increased.
Which proves the selective filtering works. It's not just that it can read the whole sequence, it's that it can ignore the 99% of noise and find the 1% of signal.
Yes. And that holds up in other areas, too. It got state-of-the-art results in audio modeling, beating bigger, more complex GAN and diffusion models. It shows this architecture is a really robust general-purpose backbone.
Okay, so let's tie this all together. What does this mean for people building or using these models? Mamba seems to have hit the trifecta. High quality from selectivity, amazing efficiency from linear scaling, and super fast inference from the hardware-aware engineering.
It really is a viable, proven blueprint for what comes after the transformer, which leads to, I think, a really interesting final thought. If the next big challenge for AI is handling ever longer sequences, entire books, hours of video, long-term memory for AI agents, does Mamba's focus on selective memory, this ability to keep what matters and efficiently forget the rest? Does that represent the core architectural principle we need to get to the next level, to scale AI beyond the limits we're facing today?
That is a very powerful thought. If the future is defined by efficiency, Mamba has completely changed the game.
I think so.
Thank you for joining us on this deep dive into Mamba.
Okay.
If there's another complex paper or a challenging topic you'd like us to unpack, please let us know in the comments. See you next time.